Sometimes when we have data on two variables x and y, where x is the independent variable and y is the dependent variable, we are interested in knowing the relationship between the two variables. In case there is a linear relationship, we have seen in a previous module how we can find the correlation coefficient between these two variables to determine or to quantify the relationship between these two. And also we have looked at the simple linear regression that we can fit to the data. In this module, we will learn how to estimate the parameters involved in our simple linear regression model and also the inference procedure that we can conduct in case of a simple linear regression. The estimation of a simple linear regression relationship involves finding estimated or predicted values of the intercept and the slope parameter of a linear regression line. Before we start with the estimation and the inference on the regression parameters, let me tell you briefly about the simple linear regression model that we have learnt in a previous model. When we have two variables x and y and we believe that there is a linear relationship between the two, then we try to quantify the strength of the relationship by first finding the correlation coefficient between the two variables. Once we find the correlation coefficient, depending on what value the correlation coefficient takes, we decide on whether we can fit a linear regression model to the data set. If we can fit a linear regression model based on the correlation coefficient between the two variables, then the model that we fit is of the form y equals beta naught plus beta 1 x plus epsilon, where epsilon is the error term. Now, in this module, we will discuss how we can obtain the estimates of the two unknown parameters in this model, namely beta 1 and beta naught. Beta naught here is called the intercept of the model and beta 1 is called the slope parameter of the regression model. The estimated regression line is then of the form y hat equals hat beta naught plus hat beta 1 x, where hat represents the predicted value of y based on the values of the variable x. Now, in order to obtain the estimates of the parameters, the method that we will see here is the method of reducing the sum of square of errors or minimizing the sum of square of error. The sum of square of error for the regression model is given by sum over I equals 1 to n e I square or epsilon I square, as we may denote the error term, where the error term is given by yi minus yi hat whole square. The error term yi minus yi hat is for the ith observation, where yi is the actual observation and yi hat is the predicted value based on the regression model. So, what we are trying to do here is minimize the sum of square of these errors. So, we are trying to minimize SSE equals summation I equals 1 to n yi minus yi hat whole square. Now, the least square regression line is that which minimizes this SSE with respect to the estimates of beta naught and beta 1. In order to obtain the estimates of these parameters, we take the derivative, the first order derivative of the SSE with respect to beta naught and beta 1 and equate it to 0 to obtain the expressions for estimates of the parameters. These equations are called normal equations and they are of the following form. When we differentiate SSE with respect to beta naught, then the equation is in the form summation I equals 1 to n yi minus n times beta naught minus beta 1 summation I equals 1 to n xi equals 0, and with respect to beta 1, the equation is summation I equals 1 to n xi yi minus beta naught summation I equals 1 to n xi minus beta 1 summation I equals 1 to n xi square equals 0. The normal equations then equated to 0 will give us the least square estimates of the regression parameters. and the expressions for the least square estimates of the regression parameters are given by beta naught hat equals y bar minus beta 1 hat times x bar, where x bar and y bar represent the sample mean of the two variables x and y, and beta 1 hat is given by summation I equals 1 to n xi minus x bar times yi divided by summation I equals 1 to n xi minus x bar whole square. We can then define the statistical inferential procedures that we perform on these estimates of the parameters. So, we have just seen how to find the best fitting regression line for the bivariate data xi, yi. We have obtained the estimates of the regression parameters using the method of least square, that is by minimizing the error sum of squares. Now, we wish to look at the method of statistical inference based on the regression parameters beta naught hat and beta 1 hat. So, to start the inferential procedure, suppose we have a set of bivariate observations x1, y1, x2, y2 up to xn, yn, where n here is the number of observations. Now, these observations could be on any of the following examples. Example 1, x could be the height of the father and y is the son's height, and we have reasons to believe that x and y are correlated. Similarly, we can have another example where x is the midterm score of a student and y is the final score. Again, x could be rainfall and y could be the yield of crop. In each of these cases, there is an underlying chance that x and y are correlated to one another, and thus fitting a simple linear regression model is appropriate. So, let us also define a few terms that we will be using in the next few slides. Let us write mu subscript y given x be the mean of response y given the value of explanatory variable or predictor variable x, and let sigma square subscript y given x be the variance of y given the value of x. Under linear regression model with equal variance, mu y given x equals beta naught plus beta 1 x and sigma square y given x equals sigma square. So, the linear relationship between the dependent y and independent x is given by y equals beta naught plus beta 1 x plus epsilon, where beta naught is the intercept and beta 1 is the slope of the regression line. Epsilon is the error term, and we assume that the error term epsilon follows a normal distribution with mean 0 and variance sigma, and the error term is represented by epsilon, where we assume that epsilon has a normal distribution with mean 0 and variance sigma square. The error epsilon I corresponding to the pair xi, yi are also assumed to be independent of each other. So, given a sample of n pairs of observations x1, y1, x2, y2, xn, yn, we use the method of least square to estimate the unknown parameters beta naught, beta 1 and sigma, and this gives us the fitted regression line y hat equals beta naught hat plus beta 1 hat x, where the least square estimates of the two parameters are beta 1 hat equals summation xi minus x bar times yi divided by summation xi minus x bar whole square, or we can see that the numerator of the estimate of beta 1 can be written as sxy, or the covariance between x and y. So, we know that the correlation coefficient r is given by covariance between x and y divided by standard deviation of x times standard deviation of y, and using this relationship we can write beta 1 hat in terms of the correlation coefficients as r times standard deviation of y divided by standard deviation of x, and beta naught hat is given by y bar minus beta 1 hat times x bar. Now, if the reader can recall, we had discussed the term residuals in connection with the outliers. In the modules where we have introduced outliers and their detection, we have discussed the method that we use to detect outliers using residuals. Now, residuals are nothing but the difference between the observed value and predicted value of the response variable. So, we can write the residuals as Ri or epsilon I given by yi minus beta naught plus beta 1 xi, which can be given by yi minus yi hat, where yi hat is represented by beta naught hat plus beta 1 hat xi. And the sample variance of the residual can be used to estimate sigma square. We call it S square, and it is of the form summation I equals 1 to n yi minus yi hat whole square divided by n minus 2, where S is called the regression standard error with degrees of freedom n minus 2. Now, there are a few conditions that we need to keep in mind before performing inference on a regression model. We have to assume that the sample is actually a simple random sample from the population. We also assume that there is a linear relationship between the dependent and independent variable. This can be checked using a scatter plot of the data. If we create a scatter plot of the data, we can see that the points are aligned on a straight line, either positive or negative, and then we can conclude from the scatter plot that there is a linear relationship between the dependent and independent variable. And based on this conclusion, we can fit a regression model to the data. We also assume for regression inference that the response variable is normally distributed, and the standard deviation of the response is the same for all values of the explanatory variable. This can be drawn as a conclusion from the assumption of linear models that the error terms are homoscedastic, or the variances of the error terms are same. Now, before we discuss the inferential methods, let me give you a brief outline of the distribution of the regression parameters. In linear regression model, one of the assumptions is that the error terms are normally distributed. We have already seen this assumption before. We assume that the error is distributed with normal distribution with mean 0 and variance sigma square. Under the above assumption, the regression parameters beta naught and beta 1 are distributed as follows. Beta naught hat follows a normal distribution with mean beta naught and standard deviation sigma times square root of 1 divided by n plus x bar square over summation xi minus x bar whole square, and beta 1 hat, which is the slope parameter, is normally distributed with mean beta 1 and standard deviation sigma divided by square root of sum of xi minus x bar whole square. Since sigma here is unknown, we use S to estimate sigma. Now, the confidence interval for the regression parameters. We fix a level of confidence alpha, and at the level of confidence 1 minus alpha, the confidence interval for beta naught hat is given by beta naught hat minus t star times standard error of beta naught hat and beta naught hat plus t star times standard error of beta naught hat, where t star is the upper alpha divided by 2 critical value of the t n minus 2 distribution, which is the t distribution with n minus 2 degrees of freedom, and standard error of beta naught hat is given by sigma square root of 1 over n plus x bar square over summation xi minus x bar whole square. And as I have mentioned before, we do not know what the value of sigma is, so we replace sigma by S. And the confidence interval for the slope parameter in a regression setup is at a level of confidence 1 minus alpha. The confidence interval for beta 1 is given by beta 1 hat minus t star times SE of beta 1 hat and beta 1 hat plus t star times SE of beta 1 hat, where t star again is the upper alpha divided by 2 critical value of the t n minus 2 distribution, and standard error of beta 1 or SE of beta 1 equals S divided by square root of summation xi minus x bar whole square. Now, the confidence intervals for the two regression parameters tell us that when we estimate the parameters, we are confident that at level of confidence 1 minus alpha, the value of the parameters will lie within this interval. The confidence interval for regression parameters to test the hypotheses that, so now that we have looked at the confidence intervals for the two regression parameters, we may now move on to the testing of hypotheses for the individual regression parameters. To test the hypothesis that individually the regression coefficients for slope is equals 0, that is the null hypothesis H naught such that beta 1 equals 0, we use the test statistic given by t equals beta 1 hat divided by standard error of beta 1 hat, where the p value for the test statistic is obtained from the t n minus 2 distribution. And the rejection criteria is if the p value corresponding to this statistic is less than the level of significance alpha, then we reject the null hypothesis that the slope is insignificant. So, we have just seen how we can test individually the slope parameter of the regression line. We can also perform a test on the intercept parameter beta naught, but however, it does not make much sense and it is not usually done in statistical practices. So, here I wish to explain with an example how we can predict the value of y, the dependent variable, given a value of x, which is the independent variable. So, I have a data set here which contains the data on two variables. One is the distance from the fire station and the other is the amount of damage that a fire has caused. Using these two variables, we use distance as the x variable, which is the independent variable, and we use damage as the y variable or the dependent variable. So, suppose we wish to predict the amount of damage of a burning house which is 2 miles from the nearest fire station. What we do is, we first use this data set and we fit a regression line to the data. By fitting, we mean we obtain the parameter estimates for this regression line and plug them back into the equation, and the equation that we have got here is y equals 10.28 plus 4.92 times x, where the slope is 4.92 and the intercept parameter is 10.28. And we wish to predict the amount of damage of a burning house which is 2 miles from the nearest fire station, which means the distance, which is our independent variable, takes the value 2. So, plugging in that value of x here, we predicted y is given by 20.12. So, for a specific given value of the explanatory variable x, say denoted by x star, we assume that the response y comes from a normal distribution with mean mu subscript y given x star and sigma, where the mean is given by beta naught hat plus beta 1 hat times x star. We can then find the estimate of the mean by plugging in the estimates of beta naught hat and beta 1 hat. So, for a level of confidence 1 minus alpha, we can again find the confidence interval for the prediction, which will be given by mu hat subscript y given x star plus minus t star times standard error of mu hat subscript y given x star, where t star as before is the upper alpha divided by 2 critical value of the t n minus 2 distribution, and standard error of mu hat subscript y given x star is given by s times square root of 1 divided by n plus x star minus x bar whole square divided by sum of xi minus x bar whole square. Now, the error in case of prediction will be larger than the error for the mean response, and the reason is that there is an extra error in estimating mu subscript y given x star, and also there is error in drawing a value from the normal distribution, normal with mean mu y given x star and sigma. At level of confidence 1 minus alpha, the confidence interval is given by y hat plus minus t star times s subscript y hat, where t star is the upper alpha over 2 critical value of t n minus 2 distribution, and in case of prediction interval, the standard error of the predicted value or the standard error of y hat is of the form s times square root of 1 plus 1 over n plus xi x star minus x bar square divided by summation xi minus x bar square. Now, in the last few slides, let me show you how I have performed these inference and prediction using R. I have first inserted the data set with the two variables distance and damage into R, and I have put them in a data frame and called it fire. And the first thing after I have entered the data in R that I do is create a scatter plot and draw an AB line through the plots to see if there is a potentially linear relationship between the two variables. And as you can clearly see from this plot, there is a fairly good chance that there is a linear relationship between the two variables. And now we have seen the use of LM function in R before, so I will just go ahead and explain the output that I have obtained by fitting this linear regression model to the data set fire using the LM function. So, when I call the summary of fire.lm, which is the LM function that we have fitted, the output gives me the estimates of the parameters, their corresponding standard errors and p-values. And we have seen from the regression line before that the estimates of the intercept parameter is 10.2779, which we had previously rounded to 10.28, and for the slope parameter, or the one corresponding to the distance variable, is 4.919 or 4.92, as we had used the rounded value. Now, if you look at the corresponding p-values for both these estimates, it turns out that both these estimates of the parameters are significant at alpha equals 0.05, which means we include both these variables in the model. Finally, we can actually obtain the standardized residuals for the object of LM. So, in order to do that, we have used the R standard function in R and obtain the residuals, which is nothing but the difference between the actual observation and the observations that we have obtained by plugging in the values of x into our fitted regression line. And when we plot the residuals, the standardized residuals against distance, which is our independent variable, we see a fairly scattered plot without any pattern, which tells us that all the assumptions of linear model holds good in this case. We also further perform the QQ norm plot, and from the plot we can see that the plotted points are on a somewhat linear trend, and thus we can conclude that the linear fit to this data was fairly good. Now, in order to extrapolate the value of y, in this case what we have done is we have created a new data frame where we insert the value of distance equals 7.3, and we wish to know what the value of y would be when distance equals 7.3. So, using the predict function in R on our LM function fire.lm, I have here obtained the confidence interval for fit, and we have obtained the prediction interval for this fit, and the outputs are given in R. In this module, we have learned how we can estimate the parameters in a simple linear regression model. The method that we have looked at is the method of least square, or minimizing the sum of square of the residuals. And we have also looked at the different methods of testing of hypotheses related to the parameters involved in the simple linear regression model. And we have also used a data set which we have called the fire data set to illustrate the estimation procedure that we can perform in R.